I want to introduce Dr. Akira Yamaguchi. Yamaguchi-sensei is a professor at the University of Tokyo and also director of Nuclear Safety Research Association. The first presentation title is the Introduction to Nuclear Power, Nuclear Engineering. Okay, yes, please, Sensei. Yes.
Thank you very much for the kind introduction, and it's a great pleasure and honor to give my point in this the great seminar we did, and I appreciate your listening and questioning to my talk. In the first presentation, I'd like to introduce the nuclear engineering. What is the nuclear engineering? What is the potential advantage of the nuclear engineering? And the specific characteristics in terms of the safety and the energy production and much more. Okay? All right, this is the simple schematic of the nuclear power station in comparison to the thermal power station. This one is a nuclear power station. The essential difference is the reactor. In a nuclear system, they use the nuclear reaction. But in a thermal power station, the chemical reaction is used. And the energy produced in the reactor is transferred to the heat transport system to a turbine to generate the electricity, right? So in here, first of all, the thermal energy is produced in the reactor system. And then it is converted to the mechanical energy. And finally, electrical energy. So we can use the potential of the nuclear energy in terms of the thermal energy or mechanical energy or electricity. And in addition, one important thing is that in a nuclear power station, we use the nuclear reaction. That means we can get the neutrons and other beams, which is also very useful in terms of the medical application and also the breeding or transmutation and others. Okay? So, yes, this is the basis of the fission reaction chain. This is a physical process. You see the reaction time range is 10 to minus 20 power in second, right? Very, very short process. Fast process. So first of all, uranium-235, when a neutron is captured and it becomes the excited state, then transition state, then fission and fragment. This is a nuclear fission, right? It will happen in very, very short period. And after that, prompt neutron will be generated. This is at this time scale. And then delayed neutron. So all this process makes the nuclear system very, very stable. And we can control the system because the delayed neutron in a millisecond order, it is generated. That is very useful to control the power. And later, I will introduce the 3 C's. Control power, and the cooling the core, and contain the fission product. And this is the first part. Control the power, okay? Another point, for the light water reactor, it is a thermal reactor. It is called thermal reactor. Why? Because the neutron energy is very low. It corresponded to the thermal environmental temperature range. That is, the first neutron, just after the fission, the neutron speed is 20,000 kilometers per second, very, very fast, high energy. And in first neutron travels inside the reactor system where a lot of water exists. And the water is used to moderate the neutron. At the same time, remove the heat from the core. Okay? Because the water molecular include hydrogen, that is useful to reduce or moderate the energy of neutron. Why? Because the uranium-235 only make a fission at the very, very low temperature or a very, very low energy. I'll touch on this point later. Okay? And another point is that when the uranium-235 fission, some neutrons, maybe 2 or 3 neutrons are generated. At the same time, the heat and also beta ray or gamma ray are generated. Okay? Again, the first neutron generated here is moderated to the thermal neutron, where we can have the next generation fission process here. That is the reactor chain system. And we can control the balance of neutron so that the reactor system is stable and the fission chain continues. Okay? Okay, what is produced in the nuclear fission? This is a typical graph of the fission yield of uranium-235. So usually uranium-235 is divided into 2 elements. So the total yield, summation, is 200% in total, because each uranium divided into 2 elements. Okay? It is interesting that the 2 elements are not the same element. There is one peak in this energy range, mass number, 135 to 45 in here. And in this peak, iodine and xenon or cesium are included in here, right? Another peak exists in here, about 90 to 100 or 110. Here, krypton and strontium and boron でしたっけ？臭素は。These elements are included, right? So this is the fission process, and usually when the uranium fission reaction happened, energy produced is 0.0253 electron volt for 1 atom. And you know, the 1 mole of uranium-235 have the massive numbers of atoms, right? So the nuclear power generation will produce a lot of energy. It is very useful for the power generation. And the next figure, this is another interesting figure. Why the nuclear fission generates beta ray or gamma ray radiation? Of course, as you know, the radiation is harmful for human, right? So we need to protect the public and also the employees, workers in the nuclear power plant, because radiation is emitted from the fission product. Okay? And in here, this is the relationship of the number of neutrons in 1 atom and number of protons. And you will see that almost the number of neutrons and the number of protons are the same. Okay? And here, the color shows the stability of the atom. The red atoms is very stable and naturally existing, these atoms, nuclei. But the blue or violet atoms are unstable. So it emits the beta ray or gamma ray or alpha, then it becomes the stable neutron. Please take a look at this figure. Uranium-235 is in here. And beyond this mass number, or beyond this number of the proton, there is no natural nuclide because it's unstable. Okay, when the uranium-235 fissioned, as I mentioned, they will yield 2 nuclei. Okay, one is a little bit larger, and another is a little bit smaller mass number. Okay, and please see this figure. The yellow line connect this 0 point with the uranium-235, and you see the stable element exists above this line. That means that if the uranium-235 is divided into 2 nuclei, they are not stable. So how can they be stable elements? Okay, one thing is beta decay. They emit beta ray, and then also neutron emission. And if the neutron is emitted, the number of neutrons reduced. So this is a reaction in this direction, right? And if the beta decay happened, the number of protons increases. So this is this direction, okay? And another thing is alpha decay. Alpha decay, the 2 neutrons and the 2 protons are emitted. So this direction is something like this. So that means the fission product after the nuclear fission of uranium-235 comes to this way or this way or this way, which makes the nuclide stable. This is the process of the nuclear fission and how the fission product become stable. Okay, I'm sorry this very busy figure, but just explain the important point. Okay, this axis shows the neutron energy, 10 mega electron volt, where the yes, 99.9% of neutron after the nuclear fission is less than 10 mega electron volt, this number, right? And the 70% of neutron is larger than 1 mega electron volt. And the 99% of neutron energy is larger than 1 kilo electron volt. So between this, most of the neutron, excuse me. Oh, what happened? Okay. Okay, this area, this is the first neutron. The neutron generated just after the fission, okay? And please look at the red lines shown here. This is the uranium, uranium fission cross-section. Cross-section is equivalent to the probability of nuclear fission. So if the cross-section is larger, probability of nuclear fission is larger. You will see the nuclear fission happen in a very low energy range. So the neutron generated at this area, at this energy range, has to be reduced to this area. So the neutron travels starting from this point and coming to the thermal energy region here. That's why we need water to moderate the neutron, reduce the velocity, right? However, there is one more thing. This green lines. This is the uranium-238 absorption cross-section. Okay? So the uranium travels from this first neutron energy to thermal neutron energy. They have to go through these peaks, absorption peaks. That is very bad things for nuclear system design because neutron is very important. We have to use the neutron for the next generation fission, the fission chain. However, the neutron are going to be absorbed by uranium-238. So the neutron balance is very important in a reactor system design. But at the same time, it is another advantage. I will talk about this later. But anyway, please understand that this is the first fission range. The modulation happened in here. And there is a resonance region here. And the neutron has to go over the resonance region to reach to thermal energy region, where the next uranium-235 fission happened. This is the neutron energy and the reaction probability. Okay? Let me explain some important things. Okay, this is the uranium-238 atom, right? As I mentioned, the absorption happened in here in the process of the modulation of neutron. First, the neutron is traveling in this direction at the velocity v, okay? And the uranium-238, it self-vibrate according to their temperature, okay? This is a thermal vibration. The vibration speed is plus v to a minus v. So what is the relative velocity of atoms and the neutron? When the uranium is moving right-hand side, the relative velocity looks like faster, right? So please imagine that this is the absorption cross-section. This peak and the absorption of neutron happen in this very narrow range of the neutron energy. However, as you see this, if the uranium is thermal vibrating, it looks like the neutron absorption, the narrow range becomes larger, wider, because the relative velocity becomes v plus v. At the same time, when the uranium is moving right-hand side, the relative velocity should be v minus v. That means when the atom, uranium-238 atom, is vibrating, the neutron absorption energy range becomes wider. That means more neutron is absorbed by uranium-238. What does it mean? It's very, very inherent safety characteristics. As you see, thermal vibration becomes stronger if the temperature becomes higher, okay? If the temperature is low, the thermal vibration is getting smaller. That means if something wrong happened in the reactor system and the fuel temperature increases, okay, we have to control the power. Fuel temperature is increasing, but take it easy. Automatically, neutron absorption increases, okay? That means number of neutron reduces. That reduces the reactor power, that reduces the fuel temperature. This is the inherent stability or safety mechanisms of the nuclear reactor system. This is too busy, and I don't want to talk a lot about this, but this is a famous four-factor formula. This explains the number of neutron balance in the first generation and the next generation. Here, the thermal neutron fission happened, and this is here the thermal neutron fission in the next generation. Okay? Between this time point, the number of neutron is shown by N1, N2, and the N3. And in this process, as I mentioned, the moderation occurs, neutron moderation. And the neutron moderation to thermal energy neutron. And at the same time, they have to go through the resonance region of uranium-238. And some neutron may leak out of the reactor core system. So calculating all the neutron balance, we can obtain the four-factor formula to express the criticality of a nuclear system. If the K shown here, this is the unity. Reactor is critical. And if K is larger than 1, it's supercritical, right? So the work we have to do, the designer have to do, is to keep the K equal to unity to have the stable fission chain process. Okay, please forget this equation. This is too difficult. But this one is important. This axis shows the water and the uranium ratio. And this curve is the K. It indicates the criticality. If K is larger, it's supercritical. So we have to reduce the power. Okay? But if K is smaller, the reactor system cannot be critical. so it is not a reactor, right? So we have to keep the K in some ranges around 1, all right? It is interesting. There is a peak in here. This figure means if water ratio, molecular number ratio of water is larger, this is here, less fuel and more water, it becomes undercritical. If there is a many fuels or no water, again K reduces. So the reactor system is critical in the range between this neutron, H2O uranium ratio. So one of the very important safety concerns is the loss of coolant accident in a light water reactor. You know the PWR, the system pressure is 170 atmospheric pressure. In a BWR, probably 75 or 80. That is much higher than atmospheric pressure. Once the pipe breaks, the water blows down, and instantaneously it turns to the vapor. That is the loss of coolant accident. And the coolability of reactor core is deteriorated, right? But this figure suggests if the water is lost in this area, the K becomes smaller because moderation of neutron never happened. That means the reactor power is automatically reduced again. That's why the light water reactor is really inherent system. If the fuel temperature increases, power decreases. If the water is lost, power decreases, right? And the next figure shows the process. So I have already explained the detail, and I may skip this, but yes, if fission increases, of course, power increases. Then temperature rises. Then automatically, fission decreases, right? If the fission decreases, the temperature drops, so the fission again increases. That is the stable mechanisms of the reactor system. All right, these are the physical characteristics of the nuclear system. What I wanted to mention is that the first neutron is generated, and it has to be moderated to thermal neutron. And during the process, there is a many physical phenomena, absorption of neutron, and leakage of neutron, and many options. But anyway, in any cases, the light water reactor has its inherent safety mechanisms in terms of the reactor power and the water volume and temperature, right? Okay, so next one is the more energy and economical related things. Japanese government has decided to use nuclear energy because we have no natural resources, no oil, no natural gas, so nuclear energy is very important. It is more than 50 years ago, maybe 60 years ago. Why? Because you will see that if we use coal as the fuel in a thermal power plant, C plus O2 generates the carbon dioxide and 4 electron volt energy, right? How about the natural gas? It generates 8 electron volt. Then, what's nuclear? 1 uranium-235 generate 200 mega electron volt. That is greater by in order of 10 to 8th, right? Mega electron volt is 1 million electron volt. So when we have the 100 megawatt electricity power plant, how much resources are needed? First of all, coal, 360,000 tons for the 1,000 megawatt electron volt power plant. This is a typical large scale, medium to large scale nuclear power plant. How about the oil? 1,310,000 tons of oil is necessary for the nuclear for the power plant. Natural gas, about 1 million tons, right? How about the nuclear? 21 tons. So only a small amount of uranium can keep the power generation for a longer time. If we once put the nuclear fuel in a reactor system, 2 or 3 years, it can be used to continue the power generation. So that is a very good advantage in terms of the energy security. We don't need to concern about the price of natural gas or oil. Nuclear system is very useful for the storage of the energy. Okay? This is one important thing. And again, these equations are the same as the previous one. However, there are several others. Fissile fuels, coal, oil, natural gas, they emit carbon dioxide. And the nuclear fuels leave fission product. This is radioactive. This is very serious disadvantage of nuclear. We have to take care of the fission product. Nuclear fuel generates neutron. It is not much discussed. However, in the first slide, I mentioned that the nuclear system, first one is a nuclear energy. Neutron generates the nuclear energy. Then it turns to thermal energy, mechanical energy, and electricity. However, the fossil power plant, it starts from thermal energy. Nuclear fuels generate neutron. So if we can use the neutron efficiently, the potential of nuclear is getting more. Okay? The nuclear power plant converts heat to work to generate electricity. We have already used the work energy, mechanical energy. It is a carbon-free electricity, right? However, we have not fully used the heat of the nuclear system. Actually, we can obtain very high temperature from the nuclear system. And the heat is not yet fully utilized. And in addition, neutron, it is also not fully utilized. So the future generation reactor system, we are going to consider the usage of the high temperature energy source and neutron. I'll talk about these things later. Okay, first one is the carbon dioxide. This is a very interesting work by the CRIAP of the Japanese Research Institute, owned by the utilities. They compared the carbon dioxide emission for many energy sources. This is the wind farm and the solar, the geothermal, hydropower, and the nuclear, LNG, petroleum, coal, thermal power generation, right? The red part is the fuel cost. So the fuel cost is very dominant for the LNG and the petroleum and the coal. The red part is the fuel origin cost. It is the direct cost. And the blue part is the other indirect cost. And as you see, the nuclear and other renewable energy, the fuel cost is very, very small comparing to the indirect cost. Okay? So this figure shows the emission of carbon dioxide in unit of gram per kilowatt hour. And it is apparent that the nuclear power, hydropower, geothermal, solar, wind farm, the carbon dioxide emission is very, very small comparing to the natural gas, petroleum, and the coal. That is very attractive characteristics. That's why the government decided to use more neutron instead of natural gas or coal. Okay? The next one is the fission product. In this slide, disadvantage of the nuclear is the fission product produced by the nuclear fission. Okay, this is the composition of the spent fuel. This is a fresh fuel, and the uranium-235, it is about 4.5% of total. And the rest of them is uranium-238. After the nuclear fission, maybe 2 years or 3 years, it turned to this composition. The uranium-238, this part is as is, the same. However, this part turned to be a plutonium because uranium-238 absorbs neutron and emit beta ray, then plutonium is produced. And the plutonium is fissile. So again, it can generate the fission, all right? And the uranium-235, this is a fissile. So the most of them will fission, but some of them just capture the neutron. And after the operation of the spent fuel, after 4-year cooling, the composition of the spent fuel is something like this. And the total is 1 ton uranium. And in 1,000 kilogram, there is a 46 kilogram of fission product. This is really a problem. And in addition, trans-uranium element, this is again the problem. This is the 1 kilogram or something like that, very small amount, but it is going to be a lot of waste in the processing, right? So the important issue in the nuclear is how to deal with the fission product and the trans-uranium elements. Okay? I'm sorry, some of them are the Japanese, but this column is a nuclide. This is a halving time, and this is a radioactivity conversion, microsievert per kilobecquerel. And this is a weight, all right? As I mentioned, this is a fission product. You will see the halving time is maybe the cesium-135, 230 million year, 2 million year, cesium-177, 30 years. And in the Fukushima Daiichi accident, this element is a major cause of the land contamination. The halving year time is 30 years. But anyway, the halving time is several, maybe 100 years to a million years older, right? In comparison, this is the trans-uranium element. The minor actinide, this is the problem. Halving time is very long, 2 million, and this is 2 million, and 7,000 years, and so on. And the toxicity of these elements is relatively high. And we want to deal with these elements for the sustainable use of the nuclear energy, right? And this figure is the radioactivity decay of the high-level rad waste. You will see this is the toxicity, radioactivity, equivalent to 1 ton of uranium fuel. And this scale is year. Okay, this is the natural uranium, and it is converted to the nuclear fuel, and started the power generation here. The radioactivity increases because of the fission product to this level. And we continue 40 years, 60 years operation. This is this period. And here we remove the nuclear fuel from the core. And it cooled down to here. And at this point, we reprocess the nuclear fuel and then keep it in some site for the final or intermediate deposition. Problem is that this is 1 million year. And usually the nuclear power plant, maybe the high-level rad waste will be maintained or kept watch for 10,000 years or 100,000 years, very long time. This is a problem. And actually, when we compared to the initial level of the radioactivity, this is the natural uranium level. It takes several tens of thousands of years, right? However, the contents of the radioactivity, when we investigate what nuclei generates the radioactivity, it is a minor actinide shown by the red lines. This is americium, curium, and the neptunium. And initially, strontium, cesium, those are dominant for the total radioactivity, right? But it decays in several tens of years, several hundreds of years. And beyond this time, the minor actinide or a transuranium element is the dominant part of the radioactivity shown here. So, some smart scientists considered we may convert, transmute these elements, nuclei. If so, we can reduce the time of the high-level rad waste drastically shorter. Okay? You understand this, right? After the several hundred years, the dominant radioactivity comes from americium and curium and so on. Again, the difficult figure, but it is a fission chain, reaction chain of the minor actinide. In this figure, this color is a fissile. Blue one are not fissile. So, if we put this colored element in the nuclear reactor system with the first neutron, it fissile and converted to the shorter halving time elements. Let's take a look at this slide. We started from the uranium-235, and the reactor core also 96% is uranium-38, and 4% is uranium-235. And of course, this fission. However, the uranium-238 absorbs neutron, and then it turned to the uranium-239, neptunium-239, and plutonium-239. This is again the nuclear fuel. We can use the plutonium-239 as a fuel of a nuclear power plant system. However, it goes to the higher numbers element, and the plutonium-241, americium-241, curium-244. These are the dominant cause of the high radioactivity of the high-level rad waste. But fortunately, these are fissile. If we separate these elements and put it in a nuclear fuel, the total amount of the minor actinide will be reduced in the long term. This is another attractiveness of the nuclear system. Okay? Why first neutron? This figure shows the number of neutrons emitted per neutron absorption. So this figure shows that if one neutron is absorbed in a nuclide or a fuel, the number of neutrons emitted, this is the number here. At least to keep the criticality, 1 or 2, these numbers are necessary, at least. You see? And this yellow line, this is a plutonium-239. And this is uranium-235. Please look at this area. The neutron emission is more than 3 or 4, right? This means we can make the most use of the neutron at the higher energy. Actually, this is the first reactor neutron energy range. That's why the Japanese government and also French and China, India, those countries are interested in the fast reactor system. Okay? By using the fast reactor and the transmutation of the minor actinide element, what happened is that the final high-level rad waste volume comes to 1/7 if we use the fast reactor process. So the final rad waste level treatment or disposal area would be much reduced. And in addition, as I mentioned, the minor actinide is converted to fission product. The high-level rad waste time, the radioactivity reducing time, becomes much smaller. Okay, this is the, let me see, 100,000 years here. This is only the light water reactor spent fuel. But if we use the first reactor reprocessing system, it comes to this line, several hundred years. And the light water reactor reprocessing system, it maybe 10,000 years. So this is one very important feature of the fast neutron system. まだ大丈夫ですかね? So, by then, I have introduced the characteristics of the light water reactor. However, light water reactor generates the fission product, spent fuel. The spent fuel is always the problem for nuclear engineering system. However, as I mentioned, if we rely on the fast neutron reactor system, there is a possibility that the high-level rad waste problem could be partially resolved. Okay? So, according to this background, the first reactor system used worldwide is a light water reactor. But currently, many countries are looking at the next generation reactor. Of course, in Japan, we are discussing those things in a government level and the research institute. And the next generation reactor is probably the first reactor system because they have the advantage shown in this slide. Okay, with this background, I'll talk about the recent development stage of various types of reactor. And currently, not only in Japan, but in the worldwide, there are a lot of discussions of the new types of reactor. One reactor type is a small modular reactor. It's because the small modular reactor, it is a compact system and a small power. So that means the construction cost and the construction period will be smaller. That is easier for the investors. And also, it can make a modular system to adjust the total power generation. That is an advantage for the small cities and remote cities and so on. This is really an interesting idea. And another thing is the next generation reactor driven by the International Atomic Agency Generation 4 Forum, Reactor Forum. Okay? So, from now on, I'll explain the PWR, BWR, and the next generation reactors and what is the good point, bad point of this design. Okay, this is the PWR. In the PWR, in Japan, we have a lot of Westinghouse designed PWR. And the French, they use all the reactor systems are PWR. And currently, it seems many PWRs are in operation. Okay, this is the fundamental system. This is the reactor core, and in the PWR, here is the pressurizer to keep the primary system single phase, water, so no vapor inside. For this purpose, the pressurizer pressurizes the reactor primary system to generate the 15.5 megapascal pressure. And the temperature will be around 300 degrees C. And another key technology is the steam generators. And of course, the purpose of the steam generator is to convert the primary energy to secondary energy to generate the high quality water vapor, to convert the mechanical energy, work energy to electricity using the turbine and the generators, right? And after that, using the final heat sink, in Japan we use the seawater. And it condenses the low quality water vapor to water and provide the water again to the steam generator. And in the PWR, the primary system should have the pressurizer and the steam generator, so the containment is a little bit bigger because it includes the more component, and also the primary system pressure is higher. Now maybe tomorrow in the nuclear safety design, I will discuss these systems. And today, in the earlier slide, I explained 3 C's. 1 C is control power. Second C is cooling core. Third C is contain the fission product, right? The containment probably should be bigger because the pressure is larger, higher, and the more components are inside the containment. Okay, this is the PWR. And the BWR is in here. Please take a look at this figure. It's very simple and economical because it is a direct system. In a reactor system, the vapor, high quality vapor is generated, and some droplet is separated in the equipment inside the reactor system, and the water vapor directly conveyed to turbine to generate the electricity. And here is the condenser and goes back to the reactor system. And it doesn't need pressurizer. It doesn't need steam generator. That's why the BWR is very, very attractive design, simple and compact, right? Okay, this is the PWR and the system pressure of the BWR is 7.1 megapascal, just half of the PWR. And the water temperature, system temperature is 287 degrees C. As the pressure is lower, the saturation temperature is lower, right? Okay, I explained the PWR and the BWR, but before that, in Canada, they have the CANDU reactor. It's the deuterium moderated reactor. Why there is the gas-cooled reactor and the CANDU reactor and light water reactors? This slide explains those things. Already I mentioned neutron collide or captured by uranium-235. Heat is generated and the neutron is generated. Fission product comes out, right? Please show this table. Circle, this means possible designs. Crossing, this means impossible designs, okay? Please get it total, yes, thank you. And this is the simple figures of the reactor system. Basic fundamental elements are fuel, first of all, and the fuel is surrounded by cladding, and the moderators are shown here, and also the coolant circulates the system. And there is a reflector surrounding the reactor system. reflector's role is to reflect the neutron, to effectively use the neutron, reduce the leakage of neutron. Okay? And outside is the shielding. And as I mentioned, the gamma ray or other radiation happen in a reactor system. Okay, this is a one more thing, control load, of course. And this is a fundamental system. So basically, we use for the neutron fission chain, we need fuel and moderator, right? And neutron, if I say. Neutron is moderated to the thermal energy regions. So uranium can contain the chain reaction. So moderator and the fuel and the neutrons are necessary key elements for the reactor system, right? And this table shows the combination of the fuel and the moderator. Graphite and D2O, this is deuterium, these are very efficiently use the neutron, less absorption, neutron absorption. So we can use efficiently the neutron with the graphite or a D2O moderators. However, light water, it absorbs some part of the neutron. That means the neutron availability is worse for the light water reactor. That's why with a graphite moderator or a D2O moderator, natural uranium can be used for the fuel. However, light water reactor, we have to enrich the fuels to 3% or 4% or 5%. So according to these reasons, some countries select the natural uranium and the D2O, or natural uranium and the graphite moderator and the gas cooled. And some countries select the light water reactor and the enriched uranium. But for the enriched uranium, we have to have the enrichment technologies, right? So this is the basis, and probably those systems are used worldwide, but probably light water reactor shown here, this is the most popular, I believe. And in Japan, most of the reactor, except some early times prototype reactor, we use the light water reactor with the enriched uranium. So this slide shows the natural uranium and the low enriched uranium. And natural uranium, as you know, uranium-235 content is only 0.7%. And the uranium-238, 99.3%. So we have to raise the content of the uranium-235 to 3 to 5%. Then the enrichment plant is needed for fabricate the nuclear fuel or the light water reactor, right? And the next slide shows the reactor vessel structures of the light water reactors, PWR and the PWR. And already I mentioned in the PWR, the system is pressurized and a single phase. So it's easier to understand, right? Single water. We can rely on the coolability of single phase water. So when we look at the history of the light water reactor development, as you know, the PWR is first of all developed because they are not sure if the two-phase flow in a reactor system can safely remove the heat or not. But in the United States, they started the borax experiment where they found that if the water vapor boils, of course, the coolability is decreasing. But what I mentioned, the inherent safety mechanisms. More water vapor, that means less water atoms, elements, right? That means the inherent safety works. So if the temperature rises, water vapor are generated, automatically power decreases. So they found that such a kind of mechanisms to stabilize the reactor power control is existing in a BWR. Then BWR and the PWR are both developed in their individual way. Okay? But as I mentioned, PWR, the reactor vessel is very simple. But the BWR, they need to several equipment in here because in a BWR, we have to obtain high quality steam to generate, to send it to the turbine. So there is a separator, droplet, liquid droplet should be removed, right? And also, there are many components in here. The control rod comes from the bottom of the pressure vessel, right? This is the typical PWR system schematics. And the PWR, the control rod is inserted from the top, and the reactor vessel is mostly simple shape. Okay, this is a light water reactor. And of course, light water reactor is very, very useful. However, we need to make sure that the uranium is continuously supplied. And currently, as you know, many countries are going to utilize a nuclear power system to make the to achieve the dual purposes of energy security and environmental concerns. And of course, not only the new countries, but the China and the Russia, and of course the other European and Asian countries, United States, they are going to use nuclear more, right? So the nuclear energy system should be sustainable. Many countries want to take the advantage of the benefit of the nuclear. And let again us take a look at the energy consumption worldwide. In Japan, we are discussing the domestic issues, energy security, energy cost, carbon dioxide emission. But when we look at the worldwide energy consumption, primary energy consumption, reality is something like this. We never stop to consume the energy, right? It's increasing. And among them, renewable is just this small part. Nuclear, this is the violet part, and the hydro is blue part. These are the carbon-free energy. Rest of them emit carbon dioxide continuously. How should I solve this problem, right? And also the consumption is increasing every year continuously. Still, this tendency will continue, right? I calculated using the carbon emission factor, and of course, this is the carbon emission, not the energy consumption. Carbon emission is also increasing, and the contribution of renewable energy and the nuclear energy, hydropower, are very, very limited, not so effective. Still, coal, oil, LNG, these are the dominant energy source of the carbon emission. And probably as the primary energy consumption is increasing, the carbon emission will be increasing in the future, at least for a decade or 20 years. Let me explain the Japanese example, because in Japan, 2011, Fukushima Daiichi accident occurred, right? We had a lot of experiences regarding the safety, nuclear design, system design, and the communication with the public, and the energy policies, and so on. It's a very tough time for these 10 years. And actually, after that, okay, this is a nuclear power, right? After that, nuclear power operation stopped almost completely. And we increased the import of natural gas. Currently, more than 90% of Japanese energy is imported, right? in terms of the energy security, it's very stupid situations. However, in these years, starting from 1985 to 2019, the carbon emission is increasing in the 1990s, but after 2000, it's almost stable, because probably we save the energy usage. And also, nuclear power plant contribute the carbon emission. Okay. Please look at the blue line here, because this one is a reduction of carbon dioxide emission by nuclear. So if we don't have the nuclear technology, this part would be replaced with natural gas, probably. That means this is the benefit of the nuclear, right? But anyway, after 2011, it's increasing because the nuclear power stopped the operation and a little bit decreasing. However, the electricity sector, it is almost the same. Although the solar power is introduced in 2011, it was 4,800 megawatt. 2019, it's 61,000 megawatt. So 12.6 times introduction of the solar energy system in Japanese electricity grid system. Maybe this is a world first or second capacity of the solar energy. Still, carbon dioxide emission is 530 megaton in 2011 and 490 megaton in 2019. So it means although the solar energy is introduced, but the solar energy is not stable in a cloudy climate day and also the night. We have to use the fossil energy, natural gas or coal or oil. So to compensate the intermittency of the renewable energy, solar, we have to prepare the thermal power plant, not in operation, but kept behind. And once the renewable energy is not available, we ask the thermal power to generate the power. That means the increase of the carbon dioxide. So that is the reason. Also, the solar power is promoted like this, but the carbon dioxide emission is almost the same. So this fact suggests that we need to re-establish the stable and economical and a good energy system with high energy security. And also, one more thing. Okay, another problem is that this part, industry, consumer, transportation type, especially the transportation part, emit a lot of carbon dioxide. Automobiles, trucks, airplane, they cannot use the renewable energy currently. So they rely on the fossil energy, oil. So this is very, very important part. And we have to need to shift to non-fissile energy. And that is the heat utilization. Okay? The electricity part, it's already over 30% is electricity is used, right? So what is the solution? This is the next generation reactors. One of the important mission of the next generation reactor. In this slide, this part is a water-cooled reactor. That is light water reactor. Okay? Light water reactor temperature range is less than 300 degrees C, around so. So this system can use the district heating and the seawater desalination. However, they cannot be used for other purposes shown here. However, if we use the liquid metal reactor, sodium cooled reactor, and the supercritical water reactor, molten salt reactor, gas cooled fast reactors, and very high temperature reactors, the potential of nuclear system is expanding. Especially in here, we can generate the hydrogen, the methane reforming hydrogen production, and the thermochemical hydrogen generation, and these could be used to reduce the carbon emission in the transportation sector. And in addition, coal gasification, and one more here. This is a furnace of the iron productions at the higher temperature. Yes, blast furnace steel making, right? But for this process, we need 1000 degrees C. Current light water reactor system can never achieve this level. So our interest is the transfer of the nuclear system experience of the light water reactor to a next generation reactor. And if these reactors are available worldwide, we can apply the nuclear system in hydrogen generation, steel making, and other things like this. In the first slide, I said the nuclear power generates electricity, heat, and the neutron. This is the heat that we have not yet utilized. If we have the nuclear system, especially a very high temperature reactors, we may achieve 1100 degrees C heat source, right? This is very attractive. And this slide shows Japanese Atomic Energy Agency. They are researching the hydrogen production technology, IS process. This is the high temperature gas reactor. It generates the 900 degrees C heat source. We use this heat source and iodine and the sulfur. We convert this circulation system to generate the hydrogen here. And currently, it is in a research phase, not in a practical use, but it suggests a future potential of the hydrogen production and extension of the nuclear system attractiveness. So, in the next slide, I will present the 6 reactor types that is discussed in 4th generation forum, next generation reactor forum in International Atomic Energy Agency. And probably more than 10 countries are participating in this program. Of course, Japan are interested in most of the system. This is a very high temperature reactor. Maybe France are interested in this system. And actually, this is the purpose of this system is to achieve more than 1000 degrees C heat source. And this is a gas reactor. And then this is not fully utilize the neutron because it is a thermal reactor. However, the high temperature heat source is very attractive, as I already mentioned in the industrial application. Okay, this is the one type, high temperature gas reactor. And this is a supercritical water reactor. And the advantage of this technology is we can rely on the available light water reactor technology, but it uses the supercritical water. So the temperature and the pressure is much higher than the conventional light water reactor. So in this context, we need the research and the development for the equipment for this system. But the engineers, professors proposed this system, claim that this is very practical because it is advanced type of the current light water reactor. Okay. And the next one, gas-cooled fast reactor. The difference of the gas-cooled very high temperature reactor is that this is a fast reactor. Fast reactor means we can make the use of the neutrons. As I mentioned, neutron can be used to generate the plutonium. It is a fuel. And also the convert the minor actinide to reduce the toxicity and the period to manage the high-level rad waste. So in this context, the fast reactor is very attractive, and Japan is interested in mostly the fast reactor system. Okay. This one is a lead-cooled fast reactor, and I think in Russia they are now constructing the Brest 300. I guess it is a lead-cooled reactor. However, in a Japanese situation, the lead is very heavy. So from the viewpoint of the anti-seismic design, it is not attractive to Japanese regulatory requirement concerns. But anyway, liquid metal reactor of the cooled by lead, we do not think about the sodium-water reaction if we use this. So next one is the sodium-cooled fast reactor. And in a sodium fast-cooled reactor, this is a fast reactor and also very feasible design. But one issue of the concern is that in a steam generator system, water and sodium are existing together in the same equipment. That may have the risk of the sodium-water reaction. So, but anyway, the Japanese developers, this is the first priority research item in a Japanese next generation reactor. Okay, this is a molten salt reactor. According to the evaluation of the IAEA, the technical feasibility of molten salt reactor is the least comparing to the other designs. But it can generate high temperature and also the safety. So the potential could be interesting, right? This slide shows the comparison of the 6 types. And I already mentioned, I think the fast reactor is attractive because it can use the neutron for breeding and transmutation. So please look at this. The first reactor is sodium-cooled reactor, SFR, and gas-cooled reactor, SFR, and the lead-cooled reactor and the molten salt reactor. And the very high temperature reactor, this is not the fast reactor, but the temperature is very high. This is the advantage. Interesting, right? And another important thing is the fuel cycle. As I mentioned, if many countries try to use the nuclear power plant, of course, the resource of the uranium is limited. So in this sense, the closed cycle will provide a new technologies that the fuel cycle is closed. In the future, long term, there is no input from the outside. We can use the uranium-238 for the next nuclear fuel. In a natural uranium, uranium-238 is 99.3%. We have not used the 99.3% of uranium, but we are using only 0.7% of the uranium-235. And if we have the technology to utilize the uranium-238, at the same time, the closed cycle will reduce the high-level rad waste. Of course, it is in a research stage, and there are many technical issues to be solved. But anyway, the closed cycle is very attractive. And the Japanese policy is a fast reactor system and a closed cycle. Of course, it is because of the energy security. Why? This figure comes from the Uranium 2020 report. This report issued in every 2 years, and it discusses the uranium resources situation and the projections. This is the price of the uranium cost from 1982 to 2018. And in 2006, 7, 8, this is the time of the nuclear renaissance. many countries tried to reuse the energy because of the harmonization of the energy security and the environmental impact. So at this time, uranium price is escalating. And then after the Fukushima Daiichi accident, it reduced. But you know, currently the uranium price is around $60 or $70, this area again. So I don't know if it reflects the actual resources balance, but anyway, the uranium cost is, of course, the uranium balance is an interesting or important element to be considered in a future energy program. Okay, this is the last slide. I mentioned closed cycle. So what's the closed cycle? Maybe France, Russia, China, Japan, those are the countries that are trying to develop or establish the closed cycle. And in the United States, there are one-through system. They use the light water reactor, and they use the fuel, and the spent fuel is directly disposed. Right? This is the open cycle. In other words, the light water reactor cycle. Here, this is the nuclear power plant and the light water reactor. And currently, to control the total amount of the plutonium is used in a light water reactor. This is the plutonium used in a light water reactor to reduce the total amount of the plutonium, right? And the spent fuel from the light water reactor is sent to the reprocessing plant here. And here, the uranium and the plutonium are extracted. And the plutonium and the uranium are mixed, extracted. And then it is sent to a MOX fuel fabrication plant. And here, the fuel is fabricated, and it is used in a light water reactor. However, this cycle does not work for a number of times, number of cycles, because the quality of the plutonium will be deteriorated if we use it in a thermal reactor. In a thermal reactor, some minor actinide will be accumulated, right? That means the long life, high-level rad waste still exists. So, what are we looking at? This is a closed cycle, or a first reactor cycle. In a first reactor cycle, this light water reactor is replaced with the first reactor. And the first reactor uses first neutron. You have already understand what is the first neutron, what is the thermal neutron. After the fission, the neutron energy is 1 mega electron volt to 10 mega electron volt. But in a light water reactor, neutron energy should be 0.1 electron volt. So it has to be moderate, reduce the neutron energy. However, the first reactor, they can use the first reactor directly. And the first reactor may be used for the plutonium generation, breeding, and also the transmutation of the minor actinide nuclei. So the spent fuel coming from the first reactor is sent to reprocessing plant again. Maybe the design of reprocessing plant here and here may be a little bit different because the fuel type is different. But the basic system is the same. The MOX fuel fabrication plant, here the MOX fuel. MOX is the mixed oxide. That is the uranium and the plutonium mixed oxide fuel. And the fuel is sent to the first reactor again. And here, important point is that the first reactor, they use the first neutron energy regions. So the plutonium quality is not deteriorated. They can convert the minor actinide to less shorter halving time fission product. And also, they can breed plutonium. So that's why we say closed. Of course, finally, after the reprocessing plant, we need to have the high-level rad waste and geological disposal facility. This is also a very critical issue. And in Japan, of course, we have not yet decided the place where the geological disposal facility is placed, located. But anyway, the total amount of the high-level radu waste will be reduced to 1/7, and also the halving time will be reduced, and probably 300, at least less than 1,000 years will be good enough to manage the high-level waste. That is a good progress comparing to the current period of 10,000 years or several tens of thousand years, right? Okay, this is the future picture of the nuclear system. Of course, light water reactor is very important technology to achieve our present goals of energy security and the environmental concerns. However, in the future, we may need to start the development of the next generation system, which will be sustainable and more people can rely on. All right, let me summarize my talk. Nuclear power plant generate heat and neutron, right? By them, we have only used the electricity, right? But there is a potential to use heat and the neutron in a future system. And the heat is converted to electricity, neutron is used for fission chain. This is a current system, but in the future, we can use heat for the hydrogen production, and we can use neutron for the reduction of the high-level radu waste toxicity, okay? The potential value of next generation reactor, it is not used in light water reactor. The high temperature media for hydrogen generation. This is a gas-cooled reactor, high temperature gas-cooled reactor. And a neutron for utilization of uranium resources. This is a breeding, plutonium production for the fuel fabrication. And the neutron for reducing toxicity and the volume of high-level waste. These are the future potential. However, we utilize only a part of the heat and the neutron. And the 6th generation for reactor designs, as I explained, and small modular reactor, micro reactors. Currently, the research area of nuclear is very, very vivid. They are trying to propose a new idea. And the probably important thing is a closed cycle, very high temperature, and the fast neutron usage, and so on. There may be any other attractiveness of nuclear system we have not noticed yet. This slide, I made this slide according to the Christensen's book of the innovation. He said this is the time, and this is the performance metric. That in a sustainable innovation, current technology is improved, modified, and the performance is increased. In the nuclear, we have generated first generation light water reactor, then second generation light water reactor, and the third generation light water reactor. And currently we say 3+ generation light water reactor. For example, EPR of France is this type of reactor. And our target is to increase the performance. What is the performance here? Economical efficiency. From the first generation to 3+ generation, the economical performance is amazingly improved. However, if the performance go beyond this user need line, the user may switch to another lines. This is a low-end innovation. And maybe low-end innovation example is a small modular reactor. Cost may be more expensive, but it presents some attractiveness that the large-scale water reactor does not have. However, there is another performance metric, I would say the example is a renewable energy. Here, renewable energy is the example. Their metric is probably a safety or maybe environmental goodness. Wait. And initially, the performance is much less than user needs. So you remember that in 20 years ago, solar energy is not popular, but currently it's cheap and the massive power is generated. So if we switch to another performance metric plane, we can develop a new technology area. This is an example of the renewable energy. So what's the future in the nuclear? As I mentioned, nuclear has a potential of hydrogen generation and the rad waste reduction of the rad waste toxicity, and so on. We have generate electricity with nuclear, but we have not fully used the heat and neutron. That is probably the future potential. And we may propose a new performance metric for the next generation nuclear system. And it will be sustainability, safety, resilience, hydrogen generation, cleanness, and so on. Okay, that's the end of my talk. Thank you very much for your kind attention.
He touched of the comprehension of the nuclear energy, including a basic of nuclear energy, such as reactor chain, Doppler effect, and safety mechanism. Also, as the benefit from the nuclear energy is fuel consumption, carbon dioxide emission, and also touch of the some type of the nuclear generation reactors. Okay, are there any questions for Dr. Yamaguchi from audience? Yes, yes.
Hello. There was a question in Slido. I'm asking that for the person. So, what is the steam temperature and pressure after the turbine in PWR, pressurized water reactor?
Pressurized water reactor.
Yes. The question is there.
あれは300度ですよね。Yeah, 300 degrees C, and the pressure is いくらだろう。やっぱ17メガパスカル。
二次系ですからね。彼が言ってるのは
アフター
ターバインだから二次系じゃないですか。
二次系ですかね。He knows.
Yeah, I'm familiar with PWR. So your question is related to after the turbine. After turbine. What you call it? Around 8 degree to normal temperature. I mean the 80 to after the condenser, the 30 or 40 degree. It depends on the seawater
and the
temperature. Pressure not so high. Not so high. 20気圧。
20気圧ぐらい。
いかないか。コンデンサーだと。
ああ、そうですね。
コンデンサーの後は上がってるけど。Okay, I have some figure, so I will show you later.
Yeah.
Okay. Are there any more common question? Okay. Yeah. Yes, please. Yes, please.
Yes. Thank you. Relika from Minister of Environment. I have a question regarding those fast reactors and the fact that they produce plutonium could be also a concern from non-proliferation perspective, since this material could be used in addition that this could be used in production of MOX fuel it could be used for nuclear weapons production as well. And can this fact jeopardize this widespreading of this type of reactors in the future? Or have this fact been considered? That currently the countries that are using fast reactors or have like tested them or developing are also mostly weapons that have countries that have nuclear weapons. But if other countries would like to start using them, could this be a problem from an international non-proliferation regime's perspective? Thank you.
Yeah. Yeah, actually, that's a very critical point. And in a Japanese reprocessing system, we extract the plutonium with the other elements. And one is the uranium is mixed with plutonium, which make the produce the nuclear weapon very difficult. And in a fast reactor system, of course, they are very much concerned about the security. And their proposal is that if we put some minor actinide in a plutonium, when they extract in a reprocessing plant, the toxicity of the minor actinide will be effective to prevent the transfer to the nuclear weapons because of its hard to access and not easy to handle. So the idea is proposed for the higher nuclear security performance. And in a Japanese research institute has compared the several types of the reactor concept and the nuclear fuel cycle concept. And they have proposed 6 metrics to evaluate the advantage, performance of the system. And one of 6 is nuclear security, non-proliferation. So it is very important, especially in Japan, important topics, but technical, by technology, we can handle it. I believe so, yeah.
Okay. Other question? No.
I have one.
Yeah, yes. Yes, please. Just please use it, Matt.
Hi. Can you explain what type of reactors are in operation or were built in Japan? I know that there are pressurized water reactors and boiling water reactors. Why? How many each? And what was the basis behind building boiling water reactors or pressurized water reactors in Japan historically?
Okay. Initially, the first reactor introduced, constructed in Japan is a Calder Hall type, gas-cooled and graphite moderated reactor from the UK. However, they have the problem of this earth seismicity because it used the block is put in a system and that is fragile to the large earthquake, and they modified the design, I think. And after that, also the economical reason, the PWR and the BWRs are the candidates in Japan here. And I don't know why PWR and the BWR are selected, but anyway, it is the demonstrated in the United States, and also already the PWR and the BWR are constructed and a good performance, and probably both designs are equally attractive, and probably in Japan currently number of PWRs and the BWRs are also the same. Maybe Hattori-san may follow up later. And in addition, another thing is that from the beginning of the Japanese nuclear program, we have concerned about the sustainable energy security. I mean, uranium resources. So we have decided to develop the first reactor. But the judgment of the government is that the development of the first reactor would take some long time. So by then, we may have the intermediate reactor, which can use the plutonium and also natural uranium, very flexible. That is the advanced thermal reactor. And it was constructed, and for 30 years or something, it continues the operation, but the demonstration reactor construction was given up. One reason is that the uranium resources is available more than our expectation. And actually, the first reactor development program is extended. It is also because the uranium worldwide, there is a much amount of uranium. So in the Japanese history, starting from a holder coal gas-cooled reactor, but the economical and probably earthquake reasons, and also we have a good relationship with the United States. They provide the technology and the fuel, and we introduced the Westinghouse PWR and the GE PWR. And then at the same time, as a Japanese own development program, we pursued the first reactor program. But in between, there is advanced thermal reactor. And currently, our time is to compare from the scratch of the every technologies for the future generation reactor. And I have already explained the 6-type generation next generation reactor of the IAEA generation 4. And except the supercritical, except the molten salt reactor, Japan participates in the international program. And in these years, the government proposed the first reactor development roadmap. And they said, 5 years we discuss and compare the system. And after 5 years, we will select the most appropriate design in Japan. That is 2023, 2 years, 1 year or 2 years after. And probably we will select the sodium-cooled or a gas reactor or some candidate. It is a history, very brief explanation of the history. 服部さん、どうして PWR かっていうのは何かありますかね? Maybe 服部さん is from Tokyo Electric Power Company and he's a good knowledge, expertise in history.
Okay, thank you. Thank you. My name is Hattori, and I worked in TEPCO for 36 years. And I'm in charge of the TEPCO has, before the Fukushima accident, TEPCO has 17 nuclear power plants in 3 nuclear power stations. I have been involved in all the 17 nuclear power, the construction and operation. And in Japan now is 33 operational reactors we have in Japan, totally. And out of 33, 17 is BWR and 16 is PWR. No BWR started operation, but out of 16 PWRs, 10 reactors restarted. And that is current situation. We have the 33, and out of 33, 10 reactors, all PWR started operation. Before the Fukushima accident, we have 54 reactors. And before that is some was shut down. And so before the Fukushima accident, around 2000 is we have 50 before 2000, 1998 is that is 57 nuclear power plant we have in Japan. 1 gas-cooled reactor and 32 BWR and 24 PWR. You might think this BWR is a little bit larger portion. That is very different from the world average. Now is almost 3/4 is a PWR in worldwide. About 400 reactors is now in operation. maybe over 300 is a PWR. And the PWR is limited, and the BWRs and gas CANDU reactors and some gas-cooled reactors, that is a total world picture. I don't know why in Japan is a BWR is the superior than PWR. I myself is working in TEPCO. TEPCO is the largest utility company in Japan. We have 17 reactors, all BWRs. And I myself my knowledge is mostly the BWR. I myself is a BWR is the best water reactor, I think. And it's very simple and very easy to operate and very economical. And I love BWR. Thank you. And I may have a chance to this afternoon, I will talking about for the history of the nuclear development in Japan. And at that time, you may ask, please. Yeah, thank you.
Maybe it's a top secret.
So the last B was boiling water.
Mm.
I think it's this water.
Okay.
Yeah, one more.
Any other? One more?
The gentleman
yes,
here.
please.
Concerning fast reactors, what is the status of Monju fast reactor right now, and do you have any perspective to use this reactor once again?
Yeah.
No. And currently, all the nuclear fuel has been removed out of the core, and it was kept in storage facilities. And the next step is the discharge the primary sodium. And some people say the Monju is still useful, and it should be used as the research facilities or some others. But actually, it is an old design, and also the regulatory requirement is tough to manage it. And currently, we have no plan to reuse the Monju reactor. But instead, we have a JOYO reactor. That is an experimental fast reactor. The scale is much smaller. Output is 100 megawatt thermal and no steam generator. But it has the fast neutron. So we can use the research and also the generation of the medical isotope productions and so on. So now Monju has been decommissioned, and the decommissioning process is going on. But the JOYO reactor, they are trying to restart the JOYO and currently discussing with the regulatory authority. That's the situation. Mm.